The Hyperbola, Chapter 10, Section 4. So a hyperbola is a collection of all points P in the plane, the difference of whose distances from two fixed points, called the foci, F1 and F2, is a constant. So remember with an ellipse that the sum of the distances from a point and from a focus to a point on the ellipse to the other focus was constant. Now the difference between a focus and a point on the hyperbola to the other focus is going to be constant. The vertices V1 and V2 are located at the intersections of the hyperbola and the transverse axis. So now that axis, what we called axis of symmetry for a parabola, is now the transverse axis. And now we have a conjugate axis. That's the axis that is perpendicular to the transverse axis, centered between the two hyperbolas. So basically the line that passes through the center perpendicular to the transverse axis. So we can see how this works. So let's look at a hyperbola where the center is at 0, 0, and the transverse axis is along the x-axis. The equation of hyperbola with center at 0, 0 and foci at negative c, 0 and c, 0. Notice again the foci are at plus or minus c, 0. So focus, see, so you can still use the same idea that we had where the focus, C, so negative C0 and C0, and the vertices are at negative A0 and A0. So again, A, that upside down V for a vertex gives us an A, so negative A0 and A0. So for the ellipse and for the hyperbola, C deals with the focus and A deals with the vertex. And they're a measurement from the center. So it follows the same thought process. And then we have x squared over a squared minus y squared over b squared is equal to 1, where b squared is equal to c squared minus a squared. Now here I will point out that the vertex is closer to the center than the focus is. So now the focus is the long side, is the hypotenuse. So we notice that our Pythagorean theorem goes back to what it was before, what we usually think of as a squared plus b squared is equal to c squared. So keep that in mind. For a hyperbola, the focus is farther away from the center. So that's going to be your long side, going to be your hypotenuse. Whereas A is going to be closer to the center, so that's going to be one of your sides. B is still going to be the other side. So all those things work out nicely together. So now if we have the hyperbola with the center at 0, 0 and the transverse axis along the y-axis, then the foci are going to be at 0, negative c, and 0, positive c, right? Because now we're transverse axis along the y-axis, so it's going to be up and down. And vertices at 0, negative a, and 0a, we get y squared over a squared minus x squared over b squared is equal to 1, where b squared is equal to c squared minus a squared. Now, again, as I pointed out with the ellipse, notice that A tracks with, in this case, the transverse axis, right? So you're always going to have something over a squared minus something over b squared. So a squared is always going to come first, but what goes over it is going to depend on your transverse axis. If your transverse axis is the y-axis, then you're going to start with y squared over a squared. If your transverse axis was the x-axis, you start with x squared over a squared. So it does matter the order you put them in. You don't want to subtract backwards. But A squared is always going to come first, and it's going to be related to the transverse axis. Well, now we have something else that we need to deal with. When you're dealing with a hyperbola, and let's see if I've got it. Yes, I do have it drawn on here. Notice these dotted lines that I have drawn on this. Those are what are called the asymptotes of the hyperbola. The hyperbola will approach those asymptotes, but never touch them. So they'll just get closer and closer and closer to it. So that's a necessary part of being able to draw our hyperbola, because we don't want to make it too wide and have it just go out too far. We also don't want to have it start curving in on itself again. So we want to have it approaching, but never touching those asymptotes. Well, how do we find the asymptotes? So if you have the hyperbola x squared over a squared minus y squared over b squared is equal to 1, it has two oblique asymptotes, and those asymptotes are y equal to b over a x and y equal to negative b over a x. Now, remember that b over a or negative b over a is giving us the slope of these asymptotes. Slope is rise over run, or change in y over change in x. So notice that b is associated with y, a is associated with x. So that's why we have b over a x and negative b over a x. If we have the hyperbola y squared over a squared minus x squared over b squared is equal to 1, the two oblique asymptotes are at y equal to a over bx and y equal to negative a over bx. Notice that a is associated with y and b is associated with x. So again, you're going to have the tables available to help you with this, but it's just a way that you can remember which way it goes. You're going to, on the top is always going to be, for the slope is always going to be what's associated with y, and on the bottom it's going to be whatever's associated with x when we create our rational functions. Well, unfortunately, we don't really get to work a lot with the center being at 0, 0. So many times we have the center at some other point. So we have HK, and dealing with that where the transverse axis is parallel to a coordinate axis. Then if that's parallel to the x-axis, the foci are h plus c, k, and h minus c, k. The vertices are h plus a, k, and h minus a, k. Equation becomes x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And the asymptotes are at y minus k is equal to plus or minus b over a x minus h. And you can see it's the same transitions or transformations that we've done for the parabola and for the ellipse. If we're parallel to if the transverse axis is parallel to the y-axis, then the foci are at hk plus c and hk minus c. Vertices at hk plus a, hk minus a. The equation is y minus k squared over a squared minus x minus h squared over b squared is equal to 1, and y minus k is equal to plus or minus a over b, x minus h for the asymptote. And for both of these, remember that b squared is equal to c squared minus a squared. And you can see my little drawings down at the bottom for that. So let's go to work interpreting this. So interpreting the equation of a hyperbola. For the find the center, transverse axis, foci, vertices, and asymptotes of the hyperbola. So we have y plus 1 squared over 16 minus x plus 2 squared over 9 is equal to 1. Well, we know that A is going to be associated with the first ratio there, and that whatever whether it's X or Y is there, that's going to give us our transverse axis, or the transverse axis that we're parallel to, right? And we know that B is associated with the second rational. So we have 16, which is 4 squared, and we have 9, which is 3 squared. So A must be 4 and B must be 3. Got Pythagorean theorem, B squared is equal to C squared minus A squared. So C is equal to the square root of A squared plus B squared. And amazingly enough, that comes out to be 5 again. Our center comes from Y plus 1, X plus 2. So we know that our center's got to be at -2, -1. Our transverse axis, we're associated with the A was under the Y. So the transverse axis has to be parallel to the Y axis. So we're going to look at our X value from our center, which is at -2. So the transverse axis must be at X equal to -2, because that's going to make it a vertical line that's passing through -2, 1. The foci, we know that C is equal to 5. So the foci X is going to be -2, but we're going to shift the center up and down by 5. So foci are going to be at -2, -1, plus or minus 5, or at -2, 6, and -2, 4. The vertices are also going to be shifted up and down. So they're going to be at -2, and then -1 plus or minus A. So plus or minus 4, giving us -2, -5, and -2, 3. And then to find our asymptotes for the hyperbola, we're going to use y minus k is equal to plus or minus a over b times x minus h. So if we plug those in, we have h is equal, well, we have y minus k was -1, so minus -1, so y plus 1. A was 4, B was 3, so we have plus or minus 4/3. And then x minus h, or x plus 2. So our slope is equal to plus or minus a over b, or plus or minus 4/3. Our asymptotes, once we plug those in, y plus 1 is equal to plus or minus 4/3 x plus 2. So we're going to have these two asymptotes that are going to go through, that are going to cross through the center, and they're going to help us get the curve of our hyperbola. Well, that's working from an equation. Let's go the other direction. Given certain pieces of information, let's find the equation of the hyperbola and graph it. So we have a center at 3, 0, a focus at 5, 0, and a vertex at 4, 0. Well, that was nice, because if the center's at 3, 0, the focus is at 5, 0, and the vertex is at 4, 0, we know we have everything nicely lined up. And what's happening is our y values are staying the same, and our x values are changing. So the transverse axis must be parallel to the x-axis. But not only that, our y value is always equal to 0. So the transverse axis is the x-axis. If we had 3, 1, 5, 1, 4, 1, then the transverse axis would have been parallel to the x-axis, and it would have been at y equal to 1. But it worked out nicely here. It was the transverse axis is the x-axis. Okay, so now we can look at that and say, okay, well, let's find some of our values. Well, our center is at 3, 0. Our vertex is at 4, 0. So the distance between those is going to give us A. So A is equal to 4 minus 3, or 1. Our focus is at 5, 0, and our center is at 3, 0. So the distance between those is going to give us C. So C is equal to 5 minus 3, or 2. So we have, now looking at this, we know that the center is at 3, 0. We have a focus at 5, 0. but we have to have another focus because there are two foci for a hyperbola. So the 5, 0 is 3 plus 2. So the other focus must be at 3 minus 2 or 1, 0. So we have foci at 1, 0 and 5, 0. Vertices, we've got a vertex at 4, 0. The center's at 3, 0, and we had A was equal to 1. So we got 3 plus 1 gave us 4. So 3 minus 1 gives us 2. So we have vertices at 2, 0 and 4, 0. We know that B squared is equal to C squared minus A squared. So B is equal to the square root of C squared minus A squared is equal to the square root of 2 squared minus 1 squared. 2 squared is 4. 1 squared is 1. So 4 minus 1 is 3. So we have the square root of 3. Remember, I told you these will not always come out beautiful. But the nice thing is, even if it doesn't come out to be a rational function, the square root of 3 is irrational. It goes on forever. It doesn't matter because where are we going to use that? We're going to use it in a denominator where the value is squared. So in the end, that doesn't hurt us at all because that square root of 3 is going to be used as b squared or 3. So now since we have the transverse axis is the x-axis, or looking at it as parallel to the x-axis, then the equation is going to be x minus h squared over a squared minus y minus k squared over b squared is equal to 1. Our center's at 3, 0, so h is 3, k is 0. A was equal to 1, b was equal to the square root of 3, so we can plug those in. We get h minus 3 squared over 1 squared minus y minus 0 squared over the square root of 3 squared is equal to 1. Cleaning that up, we have x minus 3 squared over 1 plus y squared over 3 plus 1. And yes, I left that 1 in the denominator because it keeps us in our form of x squared over a squared plus y squared over b squared. Or actually, let's reverse. Sorry, I'm looking at this and I'm noticing that there is a typo in this, that should be minus y squared over 3, not plus y squared over 3. So please take note of that on that line, that is x minus 3 squared over 1 minus. So let's see if I can draw here. Make that minus. That is not plus. Make that minus y squared over 3 equal to 1. And now that we have our generic equation for that, we can find our asymptotes. So y minus k is equal to plus or minus b over a times x minus h. So the slope, m is equal to plus or minus b over a is equal to plus or minus the square root of 3 over 1, because remember, a is associated with the first rational function, so that's going to be on the bottom. So square root of 3 over plus or minus square root of 3 over 1, which is plus or minus the square root of 3. So the asymptotes are going to be at y minus 0 is equal to plus or minus the square root of 3 times x minus 3. And now I'm going to move the pertinent information to the next page so we can graph it. So x minus 3 squared over 1 plus y squared over 3 is equal to 1. Center at 3, 0, foci at 1, 0 and 5, 0, vertices at 2, 0 and 4, 0. Transverse axis is the x-axis, and the asymptotes are at y minus 0 is equal to plus or minus the square root of 3 times x minus 3. You don't necessarily have to leave that 0 in there, the y minus 0. I do at times just because it reminds me where the center is on it, but you don't have to. So let's start plotting these things, see what we've got. So the center is at 3, 0, foci at 1, 0 and 5, 0, vertices at 2, 0, and 4, 0. Obviously, the transverse axis is the x-axis, as everything's falling along there. The asymptotes are y minus 0 is equal to the square root of 3 times x minus 3, and y minus 0 and negative square root of 3 times x minus 3. So we plot those two dotted lines to give us our asymptotes, and then we can draw our hyperbola going through our vertices and approaching but never crossing our asymptotes. And we see that that works pretty nicely. Otherwise, without those asymptotes, you really don't know where to draw the curve. We don't deal with a lattice rectum like we did with a parabola. So we don't just find 2 points. Could we technically do that? Yes, but it still doesn't really tell us how much it's opening up overall doing that. So the asymptotes tell us really where it's supposed to go and make it work out very nicely. And remember, we want to try to make sure that it's approaching the asymptotes, but not looking like it's going to cross them. And also, so it's not looking like it's pulling back away from this. If you look at my right-hand side one, you see, actually, if you look at the ends of both of these, you see it does look like they might be pulling away just a little bit from those asymptotes, but not enough that you take a quick look at it and go, oh, what's going on here? So we're not looking for perfection. We're just looking for it to have the correct appearance so it doesn't imply something else is happening. And that's hyperbola.